So where is that formula? So I'll give you the answer and then we will see how to derive it. So I wrote down the answer in the last lecture. So this is a new formula for this Euler beta function. So this looks like it will manifest the poles in both the channels, but it will have a parameter and it will look like n plus lambda. And this converges whenever the real part of lambda is bigger than 0. So it does not, the convergence does not depend on the kinematic variables. As long as you choose some lambda, it could be a complex number. This is an exact statement. This is exactly equal to the Euler beta function. And the thing to note is that there is an extra parameter here. So if you truncate, you are going to see the memory of that parameter. But if you don't truncate, the memory of that parameter goes away. So this I wanted to think of as some kind of an elasticity in the formula, which enables you to have some notion of the string world sheet, but without actually talking about the world sheet integrals. So this is where we stopped in the last lecture. And just to continue there, let's see how this formula recovers the previous two formulas that we have written there. So the first thing to note is that if you put lambda equal to minus t, then this term and this term cancels. And if lambda equals to minus t, this goes away. So this becomes 1 plus t. And that gives you precisely the first equality that I've written there. Similarly, if you put lambda equal to minus s, you're going to recover the second equality that you've put in there. And then, and it's a little harder to see, but if you take lambda to infinity, then the summand precisely recovers the third expression that I've written there. So I'll make a note of that there, that lambda equals to minus t. This recovers fixed t. Minus s recovers fixed s. And if you take infinity, and this you have to do in a, after thinking of truncating the sum, because otherwise taking this to infinity when there is a summoned summing index and there does not make sense. So this is sent to infinity when you consider a truncation, and then you consider lambda to be bigger than the truncation. This actually recovers the fixed u. Okay. So this formula has in it the picture that it has some notion of the world sheet as well as some notion of Feynman diagrams. Any questions?
This lambda has to be bigger than 0 degree apart. That's the only.
Yes.
So S and T can be whatever.
Yeah, whatever you want. Yeah. So I didn't want to, there is an example that I'm going to talk about later on, but I might as well discuss it here. So if you set S to be equal to minus half and T equal to minus half, then the numerator becomes gamma half square, denominator becomes gamma 1. And so you basically have pi is equal to sum n equal to 0 to infinity 1 over n factorial 2 over n plus half minus 1 over n plus lambda, and then this becomes 1 minus lambda minus a half plus lambda squared. So this gives you a nice infinite series formulas for pi. but because lambda is a continuous parameter, hidden in this formula are an infinite number of formulas for pi. So in particular, if you consider these limits, then you get some well-known series formulas for pi. If you put that in Mathematica, it is able to do the infinite sum completely. If you take the lambda going to infinity limit, this gives you the first ever series representation that was known to men, which goes by the name of the Madhava-Leibniz series. So lambda going to infinity gives you the Madhava-Leibniz series. So you have a family of formulas which belongs to this, this series. Okay, so how was this formula derived? And so what is it that we are trying to do? So we want to actually derive a formula that enables us to work with truncations while retaining the essential features of the string amplitudes. So in particular, I want to be able to truncate, and then I want to be able to see whether it has the correct Regge falloff up to a particular energy scale, and as well as the exponentially soft behavior that string amplitudes are known to have. So whether this series representation has that or not. The other thing to keep in mind is that each term here, so if you take this as an individual sum, this as an individual sum, this as an individual sum, weighted by this, then each of these terms converge independently. So it's not as if there's some hidden divergence and then it adds up and the divergence cancels. Each term converges independently. Okay, any questions? Okay. So how did we go about that? So first of all, I need a new kind of a dispersion relation, which actually enables us to capture the poles in both variables and introduces this new parameter here. One thing that I forgot to say is that the reason why you have such good convergence is that unlike the weight factor that you see there, which is its Pockhammers, now you see that there is a 1/n here in the summand. Okay, it is precisely because of the fact that the n appears in the denominator that you get such good convergence properties. So the first question that should strike your mind is that how on earth did we get that n in the denominator? Because the typical integrals, you'll never be able to get n in the denominator. Okay. So how do we go about deriving such a required dispersion relation? So this actually has in mind the simple picture that I've drawn there, that first of all, there should be a notion of both channels, but at the same time, there should be an extra term in the dispersion relation that enables me to deform. So the dispersion relation should start. So how do we derive dispersion relation? So in the last lecture, we started by writing down Cauchy's integral formula. We took the amplitude, we wrote down a simple version of Cauchy's theorem, and we closed the contour, picked up the discontinuities. That's how we derived. So we will start off by considering a large arc at infinity. And now there is going to be S, and somewhere is going to be T. So let the integration variable be called sigma, so it will be a complex variable. T can be anywhere else. So we want to have a kernel, and we are going to write down the kernel in this way. So let me just make sure the conventions are correct. So we are going to write it in the following way. So this has the feature that there is an S channel, there is a T channel, and then there is some extra piece. And the reason why I have added this extra piece is because if I put lambda equal to minus T, I will get rid of this term. and I will recover the fixed T dispersion relation from this. So now we are going to multiply it by the amplitude. So this is the amplitude. So there's going to be an integration variable. Now, typically what we do is, in the fixed T case, here we replaced the second variable by T, but we are not going to do that. We're going to leave that as unfixed. It'll have some properties that we will a posteriori justify. We'll call that function a function of sigma, s, and t. And in principle, it could also be a function of lambda, which I'm going to indicate like that. And the point is that right now, we are going to assume that this amplitude with this second ingredient, second f that I've put there, has the correct fall off to drop the arc at infinity. This has to be justified after doing the calculation, but let's proceed and see what we get. So let's imagine that there was such a function. So this is the contour gamma, and we are assuming that the arc at infinity contributes 0. So we just write this to be equal to 0. And then we are going to apply Cauchy's theorem. We are going to pull this inside. This amplitude could have some discontinuities. So for example, imagine that there was a cut starting from some value. So there are two kinds of cuts, one coming from the first variable and the other one coming from the second variable. So the one that is coming from the first variable we'll call the S channel cut. The one that is coming from the second variable we'll call the T channel cut. And I don't know a priori where this is, but let's imagine that it is somewhere like that. So this is the S channel cut and this is the T channel cut. The precise location of the cuts are not going to be important in the logic that we are going to follow. So there are going to be all kinds of contributions. So first of all, we are going to pick up the poles that come from these variables, sigma equal to S, sigma equal to T, and sigma equal to minus lambda in principle. So there will be the contributions from these guys. So let's call this contribution 1. And then there is going to be a contribution that comes from the cuts of the amplitude. We'll call that contribution 2. So contribution 1 is simply, let's see the conventions. It's minus m s st. And the contribution from the second term is minus m t f t s t. And in principle, there is a contribution also from sigma equal to minus lambda. So we will see if that contributes or not. But for now, we'll leave it like that. And then there is going to be the contribution that comes from the cuts. So the contribution that comes from the, so I'll use another board to write that. So let's put it up. The second contribution is going to be the contribution from the cuts. So there is going to be a contribution that comes from C1, that is the S channel cut. And the S channel cut I'm going to denote by the curly A. The curly A stands for the absorptive part or the discontinuity across that cut. And there is also the contribution from the T channel cut, which is like this. Let me leave a gap. So this is the two contributions. Everybody happy so far? Discontinuities, yes. So these A's are the discontinuity in the first variable. This AT is the discontinuity in the second variable. Okay. Now we are going to do a couple of things. So first of all, the first term, first line here, so let's write it in a different color so that we don't get confused. I will simply relabel just to facilitate comparison when I do the second line. So this is nothing but a relabeling of sigma to tau, just so that there is no confusion after the second manipulation that I'm going to do in a bit. And in the second line, this guy, I'm going to do a change of coordinates. A change of variables, I'm going to do a change of variables from sigma to sigma of tau. So that is going to give me an integral. So there will be d tau, and then this is going to be d sigma d tau. I'll explicitly denote the tau dependence on sigma because I've not told you what function that is. I'm going to determine what this function is. And here, this gets replaced by sigma as a function of tau. This also gets replaced sigma as a function of tau. So far we have done nothing. It's just a simple change of variables. And now we are going to use crossing symmetry. The fact that the T-channel discontinuity is related to the S-channel discontinuity. I'll continue using yellow. So this is still from here. So now use the fact that A of S, you're just simply using the fact that, I'll just use the fact that AT of sigma as a function of tau F. This is AS, and now we swap the variables. So what you get is minus 1 over pi integral d tau d sigma d tau. That kernel there and times A of S. Okay, let's write it out. 1 over S minus sigma tau minus sigma tau 1 over sigma tau plus lambda times A of S okay. Now we are going to demand that this equation, let's call this 1 or line 1, and let's call this line 2, this whole thing. So we're going to demand that L1 is equal to L2. We want to demand that because we want to maintain this ST symmetry in the resulting dispersion relation. So doing that is going to give me two conditions. So the first condition is d sigma d tau 1 over s minus sigma plus 1 over t minus sigma plus 1 over sigma plus lambda is equal to 1 over s minus tau plus 1 over t minus tau plus 1 over tau plus lambda. So this guy is this guy, and that right hand side is this piece, and tau should be the same thing as this function f after doing the change of variables. And finally, sigma of tau should be equal to that object there. Okay. Are the manipulations clear? Any questions? Because once these manipulations are clear, the rest is easy. Okay. So let's consider the first equation. So I will call them conditions star and double star. So so this guy can be written as, there's a trick. We are going to write this as dd sigma of log s minus sigma t minus sigma divided by sigma plus lambda. And on the right hand side, we do the same thing, dd tau of log s minus tau t minus tau over tau plus lambda. So this just becomes dd tau because sigma is a function of tau. And the solution is straightforward. It stares at you. So s minus sigma t minus sigma over sigma plus lambda should be equal to some constant times s minus tau t minus tau tau plus lambda. These, yes. Oh, that is because I wanted to relate the contribution from the S channel discontinuity to what comes from the T channel discontinuity, because I wanted the dispersion relation to be manifestly crossing symmetric. That's right, except that because of the fact that the S channel discontinuity and T channel discontinuity are the same, we are asking if there is a change of coordinates that enables us to equate the two. So it is not guaranteed that you'll find a solution to this condition. So you'll have to check the solution, whether it has all the right properties or not. So that is what we're going to do. Okay? Because right now, there are a bunch of assumptions that I've made. So the first assumption was that the arc at infinity drops. I have not justified that as yet. So we have to justify that. The second assumption that I have made is that there exists a solution of that kind. So we will need to find the appropriate solution from here. And once I have found a solution, that particular solution also has to respect this condition. So there are all kinds of internal consistency conditions that the solution that I find has to satisfy. Okay? So it turns out that in order to respect this double star condition, I will be forced to choose c equal to 1. So the idea is that I am trying to find sigma in terms of tau, because that's what I did. I wanted to do a change of coordinates, sigma as a function of tau. So what kind of an equation is this? This is a quadratic equation. This is a quadratic equation. One solution is obvious. What is that solution? Exactly. So quadratic solution with two solutions. One solution is sigma equals to tau. Now that solution is not interesting because that is going to just put the absorptive part with sigma, sigma, and sigma, sigma, and it will give you the wrong answer. So this is discarded. The other solution is much more interesting. The other solution is sigma is equal to you can write it in either in terms of sigma or in terms of tau. It doesn't matter. The solutions look the same. And when you actually invert this relation, you get exactly the same condition. So tau looks like S plus lambda T plus lambda over sigma plus lambda minus lambda. So this tells me what the coordinate transformation I was after. So the first guy, see, this solution actually tells me what F is. This implies F sigma ST, I labeled it as lambda, is nothing but S plus lambda T plus lambda over sigma plus lambda minus lambda. Okay. Now you can verify that the double start conditions are indeed satisfied. So if you actually take that function and make a replacement of sigma as a function of tau using this equation, you will indeed find that you get tau. Okay, so this I'll leave as an exercise to verify that double start are satisfied. Okay. So what was the missing piece? So the missing piece in the calculation was this piece here, sigma equal to minus lambda. So I've not told you what that contributes. So let's write out the amplitude in full glory. So the first line, so this is Cauchy. So in Cauchy, we have m as a function of sigma. So the full contribution is sigma plus lambda, m as a function of sigma, and then f of this quantity here. So s plus lambda, t plus lambda, sigma plus lambda minus lambda. Near sigma equals to minus lambda, this behaves like sigma plus lambda, m, sigma, and then near sigma equal to minus lambda, this is infinity. So if your amplitude dies off fast enough, so if this quantity goes to 0, then whatever steps we have done so far are justified. The other missing piece of the calculation is what just evaluate what these quantities are. So if you look at that, you put sigma equal to s. When sigma equals to s, it becomes t plus lambda minus lambda, which is t. So this object here is nothing but t. This object here is nothing but s. So in all, so finally, in all, we have minus 2m of st. We have used the crossing symmetry of m under SNT, minus 1 over pi integral d sigma along the now we can just forget about the second cut. We can just focus on the first cut, S channel cut. And this is equal to 0, so we can put the there's a factor of 2 which I forgot because this contribution by construction, the A contributions, the A sigma, AS contributions and AT contributions are the same. So that gives you this factor of 2. This factor of 2 comes because this guy and this guy are the same. And so this is equal to 0. So we take this on the other side. So we get this as the final answer. Any questions?
Are you sure that in this change of coordinates, the contours get mapped to each other?
Yeah, you can check it. So indeed, so here I've done a representative contour. So what happens is that you can take the usual notion that the cuts start from 4 to infinity, and you can actually map the 4 to infinity cut, and you see that it, depending on the value of S and T, it gets mapped to this finite interval. So depending on the value of S and T, the cuts actually change.
But the point is they get mapped to each other.
Yes. So after you do the transformation, they get mapped to each other. Okay, so this is the two-channel dispersion relation. So this would be eligible for the Veneziano amplitude. You can do this, and in fact, because of the fact that we started with Cauchy, working out higher subtracted dispersion relation is child's play. So suppose your amplitude did not die fast enough. What you would do is you would start off with a different sort of a this as the amplitude. So let's divide by sigma minus, so let's consider this ST, and your starting point would be just this object, so S minus S naught times T minus S naught. So I'm choosing the same subtraction point because I want the new amplitude to be still crossing symmetric. And so if it falls off like a power, you can divide by a suitable power, and then you can actually work out the higher subtracted dispersion relation. It's a standard way that we work out higher subtracted dispersion relation. Okay? So higher subtractions are straightforward. The other thing that is straightforward is to generalize this to 3 variables. So what happens in the 3 variable case is that you have 1 over S minus sigma plus 1 over T minus sigma plus 1 over U minus sigma plus 1 over sigma plus lambda. So that would, instead of this ST symmetric kernel, you'd get a STU symmetric kernel. And instead of that as the equation, you would get so instead of this, you would actually get, I'll use another color. So in the 3-channel version, you'll get another factor U minus sigma here and U minus tau here. And there, the resulting equation in sigma would be a cubic equation with one trivial solution, sigma equal to tau. And the remaining equation is actually a quadratic equation. So that will look like square roots. It will involve square roots. You can easily find them. And so the analogous dispersion relation valid for amplitudes like the Virasoro-Shapiro amplitude, which would involve square roots. I will show you the formula for the Virasoro-Shapiro amplitude, which manifests the poles in all channels, and each is individually convergent. But in principle, it can be done. And basically, as a mathematical curiosity, if you have a function that is totally symmetric in n variables with no constraints, you just get a generalization of this condition. And the solution to that would enable you to write down a dispersion relation in n variables. Any questions? Okay, so let's consider some examples because this dispersion relation is not familiar. This is usually never presented anywhere. So the ultimate goal in any of these dispersion relation is to consider a partial wave expansion. But before going there, let's consider doing some sanity checks. So example 1, m of st is 1 over st. So the absorptive part, this implies E of st is equal to minus pi delta function t. So let's just plug this in here. So right hand side is equal to integral minus 1 over pi integral d sigma 1 over s minus sigma plus 1 over t minus sigma plus 1 over sigma plus lambda. And we plug in minus pi, so that minus pi and this 1 over pi cancels off. And you have delta of sigma divided by, now we have to be careful because this t has to be replaced by that object there. So this is going to become s plus lambda, t plus lambda over sigma plus lambda minus lambda. So now integral is straightforward. So this is equal to 1 over s plus 1 over t plus 1 over lambda times 1 over s plus lambda t plus lambda over lambda minus lambda. And you can expand this. You will see that this guy here simply becomes s plus t times lambda plus st divided by st lambda. And this is precisely lambda over this object here. So that's a simple verification that indeed the apparent lambda dependence cancels off at the end of the day. There are, so this, whatever I'm presenting now is based on a paper that we put out on the archive last week. That was co-written with Arnav, who's there in the audience, and a graduate student of mine, Faizan. So if you want more details, just have a look at that paper, because there we work out even more examples, including one loop examples where we explicitly carry out such checks. So obviously the next question is to derive the series representation for the Veneziano amplitude. So let's consider m of st. So this is the Euler beta function. The absorptive part in this variable is a sum, it's a distribution, n goes from 0 to infinity, pi delta of s minus n, 1 plus t sub n divided by n factorial. We just plug this in here, and so m of st, using the dispersion, you can just read it off what it is going to be. So there is going to be a sum over 1 over n factorial, and then there is going to be, every time I see a sigma, I replace it with an n. So there is going to be 1 over s minus n plus 1 over t minus n plus 1 over n plus lambda. And instead of t here, we will plug in that object there. And that gives me this Pochhammer 1 minus lambda plus s plus lambda t plus lambda over n plus lambda subscript n. So that gives me the new representation for the Euler beta function. You can just explicitly check, take the summoned, do a summoned large n expansion that actually behaves like n to the power minus lambda minus 1 minus lambda. So as long as the real part of lambda is bigger than 0, the sum converges. And you can explicitly check that this is a property of each piece. So it's a property of this piece, and this piece separately. Any questions? So now the question that you should be asking is, what role does lambda play? So because now I have given you a way to construct amplitudes that are crossing symmetric, they're crossing symmetric, and if you look at the residues, so for example, let's focus on the residue at s equal to n. So when you have the residue at s equal to n, you can actually see that I'll replace here s by n, so that n plus lambda and n plus lambda cancels off, and you're left with 1 minus lambda plus t plus lambda, so that lambda also cancels out, and you're left with 1 plus t sub n, which is precisely the residue at s equal to n. So you get the correct residues as expected. This is by construction. And so the question is that then where do constraints come from? So what are the constraining principles for such an amplitude? So imagine that I gave you some random absorptive part, and I asked you to look at consistency conditions. So what is it that you would be looking for? So the point is that if you look at the large S behavior of a particular term in the sum, so remember that a Pochhammer with integer n subscript is a polynomial in the argument here. So imagine that you're looking at the n equal to 40 term. So that is going to behave like s to the power 40. Okay. So a particular term in the summand actually has bad high energy behavior. It is only when you sum over all the terms that the high energy behavior restores to what you expect. Okay. So in case the people who are familiar with the S matrix bootstrap story, there are these constraints that come from, which are called null constraints. So in this language, the null constraints get translated to high energy constraints. And in turn, it also gets converted to lambda independence constraint, because there was no lambda on the left-hand side. I put it in, it's some elasticity parameter, which enables me to stretch out the formula in various ways. And so obviously there is no lambda dependence here. So I should be able to take a derivative with respect to lambda and get 0. So indeed, that's what happens. So in fact, you can check that any nth order derivative of lambda of the right-hand side, you evaluate it, you sum it, it goes to 0. Okay. So how do we make use of lambda? So suppose somebody gave you just this as the answer and told you to verify whether it is the same as the Euler beta function, then what are the kind of checks that you would do? So to answer that question, let me go back to the pi formula. So pi is approximately equal to summation n equals to 0. And now let's truncate. We're going to truncate to n terms. 1 over n factorial, 2 over n plus half, minus 1 over n plus lambda, 1 minus lambda plus minus half plus lambda square divided by n plus lambda n. Now you can, once you have a formula, especially a series formula, you do the obvious thing that you're tempted to do. You go to Mathematica and then you start making plots. You make plots of partial sums. You change lambda. So then what you get is a plot like this. So let's call this pi sub n to distinguish it from the actual pi. So pi sub n minus pi divided by pi. And let's truncate n to be equal to 10. So this is pi 10 minus pi over pi. So what happens is that the discrepancy near lambda equal to 0. So remember, the condition is that the real part of lambda should be bigger than 0. So if suppose you put lambda equal to 1 by 100, the convergence rate of that particular sum is going to be very, very bad. So in fact, you get some big discrepancies here. And as soon as you make lambda somewhat big, the discrepancies go away up to a point. So this is something like 10 to the power minus 5. And then beyond a certain point, again, the discrepancies start increasing, but they are bounded. The discrepancies are all bounded. So on the x-axis, we have lambda. And it's bounded because in the lambda going to infinity limit, you're supposed to recover the Madhava series. So, and the Madhava series is nothing but 1 over 4. Pi over 4 is equal to 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. So it's a notoriously slowly convergent series. When lambda becomes large, you get this notoriously slowly convergent series, but it is convergent. And that's the reason that the errors remain bounded. So on a practical side, suppose I was doing it in a bootstrappy way. I was truncating the number of modes that I have access to. And using some bootstrap principles, I managed to fix these coefficients. The way that it would implement lambda would be to look for plateaus in the answers to see if the answer is stabilized or not as a function of lambda over a certain range of lambda. And if I find that, I would trust that solution. If I don't find that, solution is not trustworthy. Okay, any questions? So in fact, just as a mathematical curiosity, let me just make a note of it here, that you get similar formulas, lambda dependent formulas for all the Euler zeta functions. So as an example, I will make note of zeta 2. So zeta 2 now, so zeta 2 is supposed to be sum over 1 over n square and goes from 1 to infinity. But in this new representation, you have n goes from 1 to infinity, and the summand actually now has a lambda dependence. So you get formulas of this kind, and the convergence rate actually is much better than the original series. The convergence rate of this series is much better than any of the series at the two endpoints when lambda is small and when lambda is large. So similar thing happens here. So there's some optimum range of lambda for the series to converge best. Okay. Any questions? So eventually what we are going to do, and that is going to be content of the next lecture, is that we are going to do a partial wave expansion of this guy. And we're going to specify some spectrum. So you can specify integer space spectrum, or you can specify a random spectrum. And you're going to impose tree-level unitarity and lambda independence, and try to constrain the partial wave coefficients to see how what is the selection mechanism that gives you close to the string amplitude, or maybe you want to relax. You don't want to get the string amplitude. You want to get something more interesting. So what you can do to get that. Yeah. Yes. I'm sorry, what? Yes. Yeah, so you do a low energy expansion. So you get a small s expansion.
Either you
Yeah, so and then the Wilson coefficients of that small s expansion gives you the, yeah.
You've seen before, it doesn't matter where the branch points are, these are arguments, but wouldn't it matter if, say, the whole overlaps to the branch point?
Excellent. So in this particular case, that's a very good point. So in my derivation, I argued that when sigma is equal to minus lambda, this argument actually went to infinity from the solution. And I was assuming a high energy behavior where the amplitude went to 0 as the in the sort of so-called Regge limit. Okay. So in fact, one very important thing is that you see, because of what I know about this function, so now this dispersion relation is actually valid for a wider class of functions. So for example, suppose your Regge behavior, so large sigma and this function, so let me just write it out, s plus lambda t plus lambda over sigma plus lambda minus lambda. Now imagine that your Regge behavior was sigma to the power some polynomial of t. So let's rewrite the polynomial by pulling out the constant p. So f0 plus f1t plus f2t square and whatever. Okay. Now instead of t, I'm going to replace it with this. And every time I see a t, it is going to be replaced by something that looks like 1 over sigma. Okay. Minus a constant. So each of these actually gets replaced by a constant. So even if I had, say, something that behaved like f0 plus f2 t square, this dispersion relation would still be valid. So, and that's not true for fixed t. So imagine that you were given an amplitude that went like this. In fixed t, your representation would only converge along the real axis. The imaginary axis. It wouldn't converge on the real axis. Yeah, so I have 5 minutes, and in the last 5 minutes, I'm going to tell you about positivity, because once you have a dispersion relation, one game that you can play is look at specific signs of the amplitude, if there are general statements that you can make. And you can also do a low energy expansion and constrain the Wilson coefficients, try to bound them. So again, let's go back to our workhorse, which is this dispersion relation. So now we are going to put in the partial wave expansion. So A sigma, the absorptive part, we are going to expand in partial wave coefficient. So let's say we are scattering massless particles and we are in 4 dimensions. So you'll have an expansion of this kind. And this is the absorptive part, so the CLs would be positive. And what do we know about the Legendre polynomials? We know that if the argument of the Legendre polynomial is bigger than 1, then all the Legendre polynomials are positive. So this would actually need t to be bigger than 0. And that is not always available, except that now note that when we actually look at the dispersion relation, we actually no longer have 1 plus 2t by s. We are going to put in our favorite s plus lambda t plus lambda over sigma plus lambda minus lambda. So this is going to have an expansion where this, so instead of t, we are going to put in that. And now you can ask, are there any choices of s and t and lambda such that this is of a definite sign and this object is bigger than 0? So kernel is either greater than 0 or less than 0, and this condition is true. If that was true, then in that domain of S and T, your amplitude would have a definite sign. So because of that overall minus sign, if this is true, then the amplitude would be negative. And in this particular case, it would be positive. And now you can go wild, because now you have to find the domain where these conditions are satisfied, where you have a definite sign. And it turns out, so this is T versus S. You get a beautiful looking curve or domain. And I'm just sketching the domain because it looks amazing. You get a domain of this kind where the amplitude is, in this particular case, the first sign is picked up. So in this particular case, M of ST is negative. So if you look at it from a diagonal angle, this begins to look like a monster with two thin arms. So it's like, so we called it Edward Scissorhands or something like that in our paper. Yeah, so this is you can only access through lambda equal to 0. Yes. Okay, so I think I'm going to stop there. So the bottom line is that there is a new dispersion relation, and in the next lecture, tomorrow's lecture, I'm going to show you some numerical plots. So in the first half of the plan of tomorrow's lecture is that in the first half, I'm going to show you some numerics, and then I'm going to, in anticipation of next week's conference, I'm going to show you the derivation of the Froissart-Brown. And we're going to discuss whether it changes in light of this dispersion relation or not. Okay, thank you.
If not, let's thank the speaker again. Yeah, we'll have a 15-minute break.